Good morning to all. I am Dr.N.PRABHA, Assistant Professor of Chemistry, A.D.M.COLLEGE for Women, NAGAPATTINAM. Today we have go to discuss about point group and group multiplication table. This is belong to 3rd BSc Chemistry in Module 4. In this previous module, I discussed fundamental concept and significance of group theory. Today, we have going to discuss about how to assign the point group of a molecule and CV2 group multiplication table. First, we see what is meant by point group. It is possible to classify any given molecule into one of the point group. Each point group is a collection of all the symmetry operations that can be carried out on the molecule belonging to the group. Molecule can be classified into higher symmetry molecule and lower symmetry molecule based on the symmetry elements and symmetry operations present in them. All the symmetry operations present in a molecule form a group. A molecular group is called as a point group. During the symmetry operation, the center of symmetry of the molecule, or in its absence, the center of gravity of the molecules remains unaffected. Hence, the name point symmetry. How to assign the point group? What are the steps? In the first step, determine if the molecule is of high or low symmetry. In the low symmetry, molecules have C1, Cs and Ci. If it is not, means that the highest order rotation axis, that is Cn. Then to determine whether the molecule has C2 axis perpendicular to the principal axis. If so, there is n such C2 axis and the molecule is in the D set of the point group, that is dihedral angle. If not, means it is an either the C or S set of point groups. Determine whether the molecule has the horizontal mirror plane, that is sigma h, perpendicular to the principal axis Cn. If the molecule is either in CNH or DNH set of point groups. Determine whether the molecule is a vertical mirror plane containing the principal axis, that the molecule is either in DCNV or DND set of point groups. If not, means the molecule has n perpendicular to C2 axis. Then it is the part of Dn set of point groups. The next one is the improper rotation axis to determine that the S2n, that is the collinear with the principal Cn axis. If so, the molecule is an S2n point group. If not, means the molecule is an SCA point group. This is for the flow chart for the point group how to assign. First, if the molecule is linear, that is there is the two category. Next one. In the two category, that the molecule is linear. It has the center of symmetry, center of inversion. So has D infinity H symmetry. That is for the nitrogen, oxygen, fluorine and also hydrogen. These molecules have the center of symmetry and also that is the D infinity H point group. If the molecule is linear but there is no center of symmetry, that the examples of CNH, HI and carbon monoxide. These molecules have no center of symmetry and it also has C infinity V point group. In the C infinity V point group, this group can be defined in the same way that as that of the CNV group, where n is the infinity. The C infinity axis lie along the internuclear molecules, and since the molecule is linear, the sigma V plane or in the infinity in number. The order of this group is H is equal to infinity. All heteronuclear molecules and all unsymmetrical substituted linear polyatomic molecules are belonging to this point group. That is, example is HX, carbon monoxide, nitrogen monoxide, cyanide, etc. In the D infinity V point group, this group of the molecules contains that the C infinity axis. Infinity C2 axis perpendicular to the C infinity axis and a sigma H plane. Then it would be also imply that the molecule possess infinity sigma V plane and the center of inversion. So all the center of symmetry molecules are belonging to this point group. That is, homonuclear diatomic molecules are the nitrogen, oxygen, hydrogen, fluorine, chlorine, etc. All are the D infinity V point group. This is the special case of the molecules which contain more than one type of rotational axis, that is neither perpendicular to the principal axis as the Dn and the related point groups, nor bear any perpendicular relationship. These high symmetry molecules have shapes corresponding to the 5 platonic solids, that is tetrahedral, octahedral, cube, dodecahedral and ixohedral. In the tetrahedral point group, the highest fold axis in this point group is the C3 axis, which occurs in multiples. Molecules with only C3 axis and additionally only C2 axis belonging to the tetrahedral, a pure rotational point group, since they contain only proper rotational axis. All other type of elements, sigma V, I, Sn are absent in these 3 groups. That the tetrahedral, there is one example, SiCH3 4. That is 8C3. In 8C3 there is the 4C3 and 4C3 for the 1 and 4C3 for 2 and 3C2 and also identity. E is an identity. When sigma D, that the S4 is the collinear with the C2 axis, elements are added to the tetrahedral group element. We get a full point group tetrahedral dihedral, that is TD. The order of this group is the 24. In this, point group is 8C3, 3C2, identity, 6S4 and 6 sigma D, that is carbon tetrachloride. There is another uncommon point group is the TH, tetrahedral horizontal, which can be obtained by adding 3 planes of symmetry sigma H to tetrahedral group. The order of the group is 24. In these point groups are 8C3, 3C2, I and 3 sigma H, 8S6 for the example for CO, NO2 6 times. In the octahedral point group, there is another class of the cubic groups. Additionally, octahedral point groups have multiple C4 axes when compared to the tetrahedral groups. When a group contains only rotational axis, it is labeled as O group or H of this group or the 24. In a octahedral point group, that is point groups are E, 6C4 and 8C3, 6C2 and 3C2 dash or 3C4 dash. In the octahedral point group, if 3 sigma H is equal to 6 sigma D planes are added, the groups or higher symmetry can be generated. So the order of the group is 48. So that is cuban. That is in the E, 6C4, 3C2 dash, 3C4, 6C2, 8C3, I, 3 sigma H, 6 sigma D and 6S4, 8, 6S6. This is for the point group for Q bond. In the low symmetry groups, there is the no symmetry operation for this molecule, that is CH2FCl, that is in the identity and also mirror plane, and the point group is the C2 dash. In the point group is for the CHFClBr, that is in a 360-degree rotation. There is no symmetry is identified and only identity is found. In the identifying the point groups, in the ammonia molecule has the C3V symmetry. In the C3V symmetry, if the molecule has the symmetry in the order of the Cn sigma V plane, in the Cn axis, that the ammonia molecule has in the C3V point group. In the hydrogen peroxide, there is in the two forms, one is cis form and another one is trans form. In the hydrogen peroxide, that is in a cis form, has the C2V point group. That the conformation is important because that is in the center of symmetry. Next, in the water molecule, that is H2O. In the only for and the one rotational axis C2 and the two sigma V planes are there in a water molecule, but there is no sigma H mirror plane. If you cut the plane, there is the center of the symmetry. Water molecule have the center of symmetry and one sigma V plane. So that the water molecule point group of the water molecule is C2V. Next, if the molecule is linear, means that the C infinity V point group. If the molecule has the tetrahedral molecule, that is in a trigonal planar. If the molecule has a trigonal planar, that is D3H point group. If the molecule is bent or angular in structure, that is in C2V point group. The molecule has tetrahedral, that is TD point group. If the molecule has trigonal pyramidal, that is C3V, and bent or angular means that is in the C2V point group. In the trigonal bipyramidal, that is D3H point group. In Saha's projection, that is in the C2V, and the T-shape molecules also have the C2V point group. In the octahedral molecules are OH point group, and the square pyramidal molecules have an C4H, and the square planar or the D4H, and the pentagonal bipyramidal, that is D5H point groups are there. In the symmetry elements, there are the point groups and also examples are tabulated. In the sum of the point groups or the hydrogen peroxide, that is E and C3, and the water molecule in the E, C2, sigma V and sigma V dash. In the ammonia, identity and 2C3 and 3 sigma V planes are there. Hydrogen chloride, that is E, 2 sigma infinity and sigma V planes are there. In the benzene, in a benzene molecule, that is E, 2C6 and 2C3, that the point groups are present here there. Next we see group multiplication table. In a group multiplication table, the group multiplication table lists all the possible binary products of the group members. For a group of order H row and H column in the group multiplication table, each row and each column in a group multiplication table list each of the group element only once. There is no two rows or columns can be identical. In the representation, it is a set of matrix which represent the operations of a point group. The representation with x, y and z axis as basis on C2V point group. In a C2V point group, we see for the water molecule. In the identity, that is E, that is in a set of matrices 1, 0, 0, 0, 1, 0, 0, 0, 1. In the C2V plane, that is set of matrices minus 1, 0, 0, 0, minus 1, 0, 0, 0, minus 1. And the sigma x z set of matrices 1, 0, 0, 0, minus 1, 0, 0, 0, 1. And the sigma y z set of matrices minus 1, 0, 0, 0, 1, 0, 0, 0, 1. So, in the C2V point group, that the matrix is 3, minus 1, 1 and 1. The character of the identity operation in the dimension of the representation. Hence, above the 3-dimension representation of x, y and z coordinates taken separately can be shown as follows. That is x direction 1, minus 1, 1, minus 1. In the z direction 1, minus 1, minus 1, 1. And the z 1, 1, 1, 1, 1 for all the point groups. All the three are one-dimensional representation. A representation of higher dimension which can be reduced to the representation of lower dimension is called as reducible representation. In this representation, which cannot be further reduced to representation of lower dimension, are called irreducible representation. How to construct the C2V character table? The first step, write down all the symmetry elements of the point group and the group into classes. Remember that the total number of irreducible representation equal to the total number of classes. And the next one, determine the dimensions of irreducible representation using theorem. Remember the interrelationship between various group operation and use this knowledge using the orthogonality theorems in fixing the character. And the generate representation using certain basic vectors. Try out with x, y, z, rx, ry and rz as basis and also check it. First, according to the first rule, the number of classes in the group is equal to the number of irreducible representation. Let it as called T1, T2, T3 and T4 or the E, C2, sigma xz, sigma yz. In the second step, the sum of squares of dimensions is equal to order of the group. Sigma I square is equal to h. That is 1 square, 2 square, 3 square, 4 square is equal to 4. That is equal to h. So, all other one-dimensional representation, since the dimension of the representation is equal to the character of the identity operation of the irreducible representation, E must be equal to 1 in all of them. In the operation of irreducible representation, E must be equal. That is in a C2V, T1, T2, T3, T4. In the identity operation is 1. In the third step, sigma xi r square is equal to h. The sum of the squares of the character is equal to the order of the group. X e square plus x c2 square is equal to x sigma xz square plus x sigma yz square is equal to 4. That is 1 square, 1 square, 1 square is equal to 4. So, for all the irreducible representation T1, all the character must be equal to 1. So, in a T1, E is 1, C2 is 1, sigma xz is 1, sigma yz is 1. According to the fourth rule, the character of the irreducible representation of the same group are orthogonal to each other. Thus, the character must include 2 plus 1 or 2 minus 1. That is sigma xir, sigma xjr is equal to 0. T1 and T2 is equal to 0. T1 and T3 is equal to 0. Using this theorem, we can construct the partial character table as shown. That is C2V. That is E, C2, sigma xz, sigma yz are the point groups, and the T1, T2, T3, T4s are the irreducible representations. In the T1, that all the values are 1. In the T2, E is equal to 1, C2 is equal to 1, sigma xz is equal to minus 1 and sigma yz is equal to minus 1. In the T3, E is 1, C2 is minus 1, sigma xz is equal to 1, sigma yz is equal to minus 1. In the T4, that is 1, C2 is C2 and sigma xz is equal to minus 1, E and sigma yz is equal to 1. This is for the construction for the C2V table for the water molecule. And in the Mulliken scale of rotation, we can change that the irreducible representations in the T1, T2, T3, T4 are changed into A1, A2, B1 and B2. Thank you.